Hi, Pre-Calc. Ms. Lauschke here. I just want to finish these notes so that we can move on with our stuff. So we ended right here where I was going to give you the height or the position function. Negative 1/2 g times t squared plus v sub 0 times t plus s sub 0. And the g is for gravity. So that is your gravity. The v sub 0 is your initial velocity. So if you threw something out of a window and it started falling, free fall, right? But it had an initial velocity because you threw it. Or did you just hold it and then drop it? Then it would have had no initial velocity. This is your initial height. So if you were 100 feet up, that would be 100. Just to remind you that on Earth, gravity is either 32 feet per second squared or 9.8 meters per second squared. These are the two most used equations. Because it's in feet or meters, okay? So, you could change it into inches or whatever you wanted from there. Okay, so vertical velocity, negative g, that's the same g for gravity, t plus v sub 0, that is your same initial velocity. So what I did on my paper is I just highlighted these gravity I guess equivalencies, right? And then it tells you that your v sub 0 is your initial vertical velocity of the object and your s sub 0 is your initial height of the object. So I guess I just did not need to write those, but I did anyway. Okay. All right, so now let's go on to our application problem. So our application problem, it says the Surfside Little League uses a baseball pitching machine to help train players to catch a high fly ball. It throws baseball straight up with an initial velocity of 36 feet per second from a height of 4.5 feet. Find an equation that models the height of the ball t seconds after it is thrown. So you're going to be using this height equation. So s of t equals negative 1/2. Since this is in feet, I'm going to use g equals 32 feet per second squared as my g, because I'm just taking this equation up here and I'm basically putting in all the things that we know. So this would be t squared plus, it says the initial velocity was 36 t, and then plus they said that the initial height was 4.5 feet. Okay, so that's your equation. I would probably just simplify this very first term, negative 16t squared plus 36t plus 4.5. And then for part B, what is the maximum height the baseball will reach? So actually what I did is I did part C first. So I said do C before B because, and you'll see why, but let's look at C. How many seconds will it take to reach that height? So basically, how many seconds will it take to reach the maximum height? So let's start by putting this in our calculator. So I'd like you to just go ahead and stop and put it in your y equals. This should be your 4.5, and the function, there's more of the function, but when I put this in my calculator, I think I gave it like I don't know, 10 seconds. I went from like 0 to 10. Oops, I think I went from 0 to 10 because this is not 10. Don't you just love it? You know, but if you make your x min 0 and your x max 10, and then you say zoom 0, that's zoom fit. It will give you, and it might be better if you make it like 5 or whatever, because it falls pretty quick. Like 10 seconds is a lot of seconds. I think it falls pretty quick. So -16, I wish I had one of these on my iPad and I don't. X squared plus 36x plus 4.5. I want to go to window. I want to go from 0 to 10, and then I want to hit zoom 0. And what it should do, and it didn't, let's try 0 to 5 and hit zoom 0. Yeah, that's better. But now what we want to do is go to window, and we want more y values. So we want to adjust our y maximum. And we want our y minimum to be like -5. And then our maximum, let's make it, I don't know, 50 or something like that. So -5 to 50 gives you a really good picture of it. So y min -5, y max 50. That was after you did zoom fit, because it really didn't give you a good window. So if you want to just put this window in and hit graph, you could do that too. But so now you've got a picture of this, and it looks just like the picture that I have drawn for you. And what we're going to do is, we know that this is a downward facing parabola. We know that this is the vertex, okay? And so I know that this x value is -b/2a. So if that x value is -b/2a, and here's my a, b, c, so my a is -16, my b is 36, and my c is 4.5. If I do -b/2 times a, I'm going to get positive 36/32. And then if I reduce that, what are they both divisible by? They're both divisible by, I know 2, also 4, but I'm just trying to think, is there anything else besides 4? No, it looks like 4 is the one. So this reduces to 9/8. Okay, so at x equals 9/8, what is my y value is what you should be thinking also, because we're trying to solve b and c at the same time. How many seconds will it take to reach that height? It's going to be 9/8 seconds, and when you put 9/8 in, you get 1.125. So 1.125 seconds it's going to take to reach the maximum height. So how many seconds will it take? 1.125 seconds. I'm sorry, this is not pretty. Yours can be prettier in your, and really that work is what gave you this, right? So if you were showing your work, it would be this all the way to the 1.125 seconds. And then what is the maximum height at 1.25 seconds? So that's when we would actually calculate S of 1.125. So negative 16 times 1.125 squared plus 36 times 1.125 plus 4.5. And when we put that in our calculator, we're going to get 24.75 feet. So the maximum height that the baseball will reach, that means that this up here is 24.75, because that is the highest point there. And so do you see how we needed C to get B? Okay, so now, how much time is the ball in the air? So what we need to know is, like, when, right here where I'm putting that dot is going to be where, I'll do it in blue. That time, that t value will be how, from 0 to this t, that's how long the ball was in the air. Because this is going to represent hitting the ground, because this is the distance, right? So it started out at 4.5 feet above the ground, and this is modeling how high it was going, and then it started dropping back down. And when it hit 0 again, that's when it hit the ground. So how much time was the ball in the air? I want to find the 0 here. So I want to find the 0 on my calculator. You could also find the 0, but you would have to set, when I say find the 0, I'm talking about the y equals 0, when is your y value 0? So we're trying to find, for what t value is the y value 0. So do you see how this, setting this equal to 0 is the same thing as finding this on your calculator? And you can see how that's not an easy function to graph or sorry, not to graph, to factor. We want to look at our graph. And so I would do second trace. And I was going to write out the word second, but it's the blue second on your calculator. And then it's the calculate. Well, it's the trace key, which says calculate on top. Shoot. Sorry, guys. I'm trying here. Trace, calculate. So the second one is the blue key. And when you hit that blue key, it actually takes you to calculate, which is on top of the trace. So second trace, and then you get a menu, and you pick number 2, 0, because we're going to find the 0. And then it asks you for the left bound. You need to find your cursor. Okay, your cursor is probably going up and down this graph here. I just moved my cursor like right there. Okay, that's going to be to the left. That's my left bound. So if you move it there and hit enter, and then move it down, the right arrow moves it down here, and this would be your right bound. So once I move it down below the x-axis and hit enter, then it says guess. If you want to, you can move your cursor like right on the 0 that you're talking about. And so left bound, enter, right bound, enter, guess, enter. Okay, and it should give you a t value of 2.36, and I would round that 8 to a 9 because it had a 7 after it. And I typically ask you to go 3 places behind the decimal point unless it was otherwise given to you. So the ball hit the ground in 2.369 seconds. Okay, so it was only up for 2.369 seconds. And then part E, determine its vertical velocity when it hits the ground. So we're going to take that velocity equation, negative g times t plus v sub 0, and it's going to be negative 32 times t plus 36. That's going to be our vertical velocity. And so I want to find v of 2.369 because it said, what is it when it hits the ground? Well, it hits the ground at that second. So that's going to be negative 32 times 2.369 plus 36. And if you calculate that, you're going to get negative 39.808 feet per second. Okay, so that would end up being your vertical velocity when it hits the ground. So it hit the ground at basically negative 40 feet per second. So I would not have been wanted to be under that baseball. Okay, so now this one, I'm using the new notes. What I did when I took the notes on this problem, I got a piece of paper out and I drew those graphs. I drew them because I was like, well, we don't have these graphs. What am I going to do? So I don't know if you did the same thing or not, but I mean, it wasn't so easy. It wasn't very easy, but I did it. And I thought that it helped me whenever I was trying to solve it. So, because I need to see what they're talking about. I can't just keep going back and looking at that like that. So I thought that was it was a good idea to just turn your video off, and you're going to have to learn how to do this because this darn unit is going to be a little bit different because we didn't have the right notes copied, but I went ahead and just sketched this, so but look at this. This is distance on the y, and this is time on the x. So it starts at 0, 0. So after 30 minutes, it had traveled 30 miles. Okay? So it's called a position versus time graph. It shows the distance an object travels on the interval. This is from 0 to 150. Okay? So when is the particle at rest? Well, so what you can see is that it's like, okay, this is over minutes. It's like traveling. It stays at 30 miles away from 30 to 50. It stays 30 miles away. So that means that it must be 30 miles away at rest. So when is it at rest? Well, it's at rest between 30 and 50. Then it starts going, now it's looks like 30, wait a minute. I said after 30 minutes, this is 15 miles away. Oh, I guess I didn't look at that right because it wasn't, my eyes are bad. So it was 15 miles away. So it stayed 15 miles away. Then it started moving again, okay? And it moved to 35 miles away. And it stayed at 35 miles away. That means it's just, it's just resting from 60 to 80. So we'd say also from 60 to 80. Then something weird happens. It's 35 miles away, but look, it starts getting closer back to where it started. So after, at 110 minutes, it's only 10 miles away now from its starting point. So actually right here, it must have turned around. and decided to go back, right? Because it stayed 35 miles away, then all of a sudden it starts getting closer instead of further away, okay? Then it's 10 miles away, and it stays 10 miles away from 110 minutes to 120 minutes. So that's another time, from 110 to 120 that the particle was at rest, right there from 110 to 120. Then it keeps coming back, and now it's back home, or back to where it started. So these are your three answers. You could have also written it as intervals like this using interval notation. Okay, either one works. When is the particle moving to the left? Okay, so we're going to talk about, so it's moving distance away. Let's say that it was a starting point at 0, 0 on the x-axis, okay? And let's say that, this is representing miles. So it's like 30 miles away, 15 miles away after 30 minutes, right? And then it moves, it stays 15 miles away, but then it eventually starts to move and it gets to be 35 miles away from where it started. Remember, this is its starting point, was like 0, 0 on the number line. So let's pretend like this is just a particle that's moving along the number line. And it moved to 15, it stayed there for a little bit, and then it moved all the way to 35, right? Stayed there. And this whole time, it's moving to the right. So it moved to the right to 15. Then it moved to the right to all the way to 35. Then it stayed at 35 for a while. But then when it turns around, now it's moving left, right? It's moving left all the way, and then it went to 10. It got to 10, and it stayed there for a minute. So this is all left-hand movement. So the particle is moving left from 80 to 110. And then again from, it stays there for a minute, and then it starts moving left again, because it stays there, starts moving left again, and then it's back home. So also from 120 to 150. And then when does the particle change direction? Well, we said that it changed direction at t equals 80 minutes. Right? This is right here where it decided, you know what, I'm going back. And that was at 80 minutes. So that was position versus time. Then you have velocity versus time. So again, on these graphs, you want to look at what is your y-axis, what is your x-axis, so that you know what's going on. Here, what is your y-axis, what is your x-axis? So that y-axis is a rate of change. Okay, that's really important that you pay attention to that this is a rate of change. That means, miles per hour, meters per second, whatever, who knows what it is. This one happens to be miles per minute, but that's a rate of change. This one was not a rate of change. This one was just miles, okay? So it wasn't a rate. It wasn't like miles per something. This one actually was a rate. So velocity versus time graph. When is the particle at rest? Well, look at this graph. I mean, it's like these little line segments here. There's one, there's one, there's one, there's one, there's one, there's one, there's one down here. And technically, this can be a solid dot, but this should be an open circle. That should be an open circle, 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 and then at the end, solid dot. That's what that looks like. Solid dot at the beginning and at the end, but all the rest of these are open circles, okay? So when is the particle at rest? Well, when you have zero velocity, you are not moving at all. So look, zero velocity, is from 30 to 50. So 30 to 50, zero velocity. Zero velocity, 60 to 80. And zero velocity here from 110 to 120. Okay, and again, you could have written those using interval notation. When is the particle moving to the left? Left-hand movement is going to be when your velocity is negative, because your velocity is a directional indicator. So if it's negative, that's left-hand movement. So this is between 80 and 110. This is also left-hand movement between 120 and 150. And when does the particle change directions? Okay, so when when it's positive, it's going to the right, then it stayed, then it went to the right some more, then it stayed, then it turns around. So it changes direction at 80, at t equals 80 minutes. And like I said, you can tell because it goes from being a right-hand movement, a positive velocity here, to this negative velocity here, okay? So right there at 80 is where it changed. All right, so now looking at the two examples above, what similarities do you notice between the graphs? In other words, how do they relate to each other? So it's so weird because I noticed that my answers to when is the particle at rest and when is the particle at rest were the same. But I was using a position graph, the other one I was using a velocity graph, and then I noticed that, wait a minute, could this be, like, look at this, these are when it was 0. That's like the slope of my tangent line, maybe, because why would this be 0 unless it was like the slope of a tangent line? And then I thought about, well, what is the slope of this line? So I rose 15 and I ran 30. So the slope for this one, I rose 15, I ran 30. That's 1/2. Was my graph here 1/2? Look at that, it's 0.5. So, okay, that does kind of make sense. I'm going to take those off. That does kind of make sense that is... that would be my slope, then that would be my slope. Then what about this? Is my slope 2 for that next piece? Let's see. I'm going from here to here, so I'm rising 35 minus 15. So I'm rising 20, and I'm running 10. So 20 divided by 10, that is 2. And look, for that little brief between 50 and 60, it was 2. And then it went 0, but then what about 80 to 100? It looks down here like it's about negative 0.8. So if I did rise over run from here, I would rise another, let's say, from 10 to 35. So that would be 25, right? But then I'm going to go negative 10, 20, 30. So for that slope, I rise 25, I run negative 30. So this is going to be a negative 5/6. And negative 5/6 is 0.8. So that does make sense. And then 0 again. So that matches right here with this 0. And then from 120 to 150, I would rise 5, 10. I would run negative 10, 20, 30. So rise of 10, run of negative 30, that's a negative 1/3. Is this negative 0.3 for that one? Actually, I did 15 to 30, but it might have been a little bit of a different graph. Because right here, if I'm looking right here, I'm rising 5, 10, and I'm running 10, 20, 30. Yeah, I think this graph might be different than what she had on her paper because I got 1/2. Or maybe I didn't. Wait, between 120 and 150. I don't know. The one I drew on my paper, I got negative 1/2. And now I'm getting negative 1/3. So this one does look more like negative 1/3. So this one looks right for what we're looking at here. Okay? But so we just analyzed that and we're looking for similarities and, you know, how they relate to each other. So what I put was I put figure B represents the velocity or slope of the graph in figure A. And basically that's, you know, the gist of what I got. So that makes me think that, you know, the velocity, that if I took the distance and I found the slope, I would get velocity. Okay, if I took the slope of distance, I'm going to get velocity. That's kind of what that tells me in my mind. All right, and I think that was it. I think that's all we did on the 2.1 video. I hope that helped. We'll talk about 2.2 tomorrow. I can also do a video on 2.2 homework if you want me to, so I might do that.